the sessions that we had earlier, about 2 or so weeks ago. But this is now the fourth session that we're having, and this session will be facilitated by our master teacher, Mr. Imron Miller. He has been teaching chemistry for over 20 years. He's presently a master teacher. He has conducted teacher training sessions online, and he is the HOD of Science at Campion College, right? He holds BSc in chemistry and an MPhil in chemistry. And of course, he is a married gentleman, having 3 children, married to Madine, all right? So help me welcome Mr. Miller, who will take us through electrolysis. We are also streaming live, so you can look for Chemistry Camp day 4 online for this session. Mr. Miller, over to you.
All right, thank you, Dr. Campbell. Good afternoon, colleagues. Good afternoon, students, and welcome to our camp on electrolysis. So I'm going to be sharing with you some of the major concepts or the major concepts in electrolysis. And of course, we'll be going through some questions of the kind that you might see on your exam. Now, of course, by this stage, your teacher would have gone through the content, but I'm going to go through still, but a little bit quicker than you would experience at school, of course. And what we will do is spend most of the time tackling questions. So I hope we can have a productive time, and please do not hesitate to share your questions and your comments in the chat. And you can raise your hand as well. Dr. Campbell will facilitate you and we will hear your questions. This is the time to ask questions. You don't want to have them to ask in the exam, okay? All right, so what I'm gonna do, I'm gonna start with just a quick little Google slide on electrolysis, just taking you through the process, the basic concepts, and then we will look at some questions after that, okay? All right, so I am going to share screen. So let me know what you're seeing here.
Someone is asking if you can speak a little louder and if you can increase your volume.
All right, let me try and increase the volume on my device. Okay. Yeah, I think it's top volume, you know. All right. Yes, yes. Are you hearing? Let me know if you're still not hearing well.
We're hearing, it's just that you probably sounded a bit low, but
okay.
Continue.
All right, I'll try to increase the volume, put on my real
teacher's voice.
Yeah. All right, so there you go. You had the introduction already. Just to say that I have a YouTube channel that has lots of videos on some of the topics that you'll be getting on the exam, so you can check that out, Kim Cracker on YouTube as well. So let's get on with it. All right, so at this stage, at some point during your science career up to this point, you would have been introduced to materials that conduct electricity and others that don't. So I would expect that everybody knows some common materials that conduct electricity and some that don't. Could you type in the common chemicals that conduct electricity? Some liquids, for example, solids that conduct electricity. In the chat, quickly. Type in some common substances that conduct electricity.
I'm not sure why you sound a little.
My sound is off?
No, man, your sound is fine. It just that it sounded probably it's buffering or something. You were breaking up. Okay, so we have in the chat molten sodium chloride.
Okay, very good.
The graphite, metals, iron, hydrochloric acid. Sodium chloride again.
Okay, good. Yes. What about some insulators, some material that are insulators that don't conduct electricity? Can we have some of those?
Okay. Plastic.
Yes.
Rubber. Is that a
Very good.
somebody
Rubber.
says bottle and wood.
Okay. What kind
And
of wood?
well, just well.
Dry wood. Okay.
Styrofoam.
Yes. Somebody said sulfur.
Yes,
Okay,
someone
good.
said sulfur. Glass. Oil.
Glass.
Not sure.
Yes.
Oil. Oil is there.
Good. All right. So we have an idea. We have an idea. All right. Yes. So we can press forward. So we know the basics. We have to know about the conductivity of materials. All right. So we have what we call, in terms of electricity, we have what we call metallic conductors. Those are conductors that conduct via the movement of electrons. Right. So if we understand electricity as the movement of charged particles, you can have two types of charged particles carrying electricity. You can have electrons, as in metallic conduction, which occurs in metals and graphite. And you can have ions, that's free moving ions, which occur when the ions are in the liquid state, whether in the molten, melted, same thing, or in the aqueous state, that is dissolved in water. All right. So though that is called electrolytic conduction. Right? Liquids that conduct electricity are called electrolytes. All right? And so that is where we are now. We are looking at passing electricity through electrolytes. That is what electrolysis is. The electrolysis, as you can see there, as you probably know, is the breakdown of a substance using electricity. Lysis meaning breakdown, all right, and electro from electricity. So we're breaking down a substance using electricity. All right, good. All right, so that is what we're going to be looking at, electrolysis. And as we said, there are two types of electrolytes. You have molten ionic compounds, melted, or ionic compounds dissolved in solution. All right, aqueous ionic compounds. All right, good. All right, now we are going to look at the first type of the molten ionic compound, electrolysis of the molten ionic compound. And it's the easiest scenario because in this scenario, you have only two ions present. So for example, if we look at molten lead 2 bromide, right? What we have is lead 2 ions and bromide ions, right? We don't have any other ions. All right. And you should know the typical electrolysis setup. All right. You should be able to sketch this diagram like this. Maybe not the exact same one, but you know, some sort of container with 2 electrodes dipped in it and then an electrical circuit. All right. And you should know the basics about your electrical circuit. You should know that you should know what represents the battery or the power supply. And you know that the long one represents the positive end, the short one, the negative end. All right. So if this one is the positive end around here, then this electrode is the positive electrode, is called the what? It's a positive electrode called electrolysis. Type it in the chat. All right. And then this one is the negative end, comes around, touches the negative electrode. That is called the, yes, what we have in the chat.
I'm seeing anode.
Anode for the
Or
positive.
positive. Yeah, and I
Right.
suppose, yes. And cathode is
And
coming after.
yes, and cathode for the negative. Very good. All right, good. Yes. So there you go. All right. And you should be able to do a typical labeling. You should be able to label your electrolyte, your anode and your cathode, and your power supply or battery. All right. And you should know about the common things like that you put in there, like a bulb or ammeter or voltmeter. All right. So you should be able to do that. Of course, you see there, this container is being heated because, of course, this is a salt and they typically have high melting points. You have to heat it strongly to get it, keep it in a melted state. All right, good. All right, so we have the electrodes, we just defined them. We said the anode is the positive terminal of the cell, right? And anions go there. Because anions are negative, they're going to be attracted to the anode. They're going to travel to the anode. So anions go to the anode. Very simple. And then on the other side, cathode is a negative terminal, all right, of the cell, and the cations go there. They are attracted to it. Cations are attracted to the cathode. Yeah? Yes. Yes, ma'am. All right. So you also have two types of electrodes, right? And for us, we're going to be concerned with mainly one type, right? But you have two types. You have what we call inert or unreactive electrodes that don't take part in the reaction. And the inert electrodes that we typically use are carbon in the form of graphite and platinum. But of course, graphite is more popular because that's much cheaper than platinum. All right, so you must know your inert electrodes, carbon or platinum, or graphite for carbon, okay? Specifically. Right, so let's talk about what's happening now. Now, at the cathode, what we said, cations go there. Lead 2 plus ions, in this case, of the lead 2 bromide. It's going to go to the cathode, where they will receive electrons, right? And become discharged. So Pb2 plus has a charge of 2 plus, that means it needs 2 moles of electrons to form 1 mole of lead. There you go. And there is your half equation, your ionic half equation. Okay? So Pb2 plus 2E gives you Pb. So the Pb2 plus is discharged. It loses its charge. All right? And so it says molten globules of lead are formed at the bottom of the crucible. All right? Good. So that's what happens that's what happens at the cathode. Cations go to the cathode, receive electrons, and are discharged. That's the modus operandi. All right? And at the anode, anions go there. All right? And the anions give up electrons to the anode. All right? So they give up electrons to the anode, and the anions become discharged. So you form a neutral molecule here in this case, right? And 2 electrons. Of course, each atom gives up 1 electron, and then the 2 atoms join to form a bromine molecule. Because bromine exists as Br2 diatomic molecules, then we write it like this. Instead of writing Br goes to Br plus E, right? 2Br minus goes to Br2 plus 2E minus. All right? Everybody okay with that so far? All right. So of course, bromine is a reddish brown gas. All right. So that's what you would observe around the anode. All right. So just to go through pictorially what happened, right? The lead ions went to the cathode, the bromide went to the anode. All right. All right. So overall, what is happening is that lead 2 bromide is broken down into lead and bromine. That's what is happening overall. All right. All right. So the bromide ions give up electrons to the anode. All right. The electrons are going to travel around, see, the circuit to the cathode. All right. Around she goes to the cathode. Around to the cathode. All right. This is taking, and it reaches the cathode now, and those electrons are given up to the cations, that are the lead 2 ions, and you form the lead. The bromine atoms form bromine. Lead is going to fall to the bottom and so on. All right, little quiz. The electrolysis of iron 3 chloride yields iron metal and a gas. What is the color of the gas produced? All right, type it in the chat quickly. What is the color of the gas produced?
Okay, so person they're saying C.
All right, people are saying C.
Yes.
So that means that you're assuming that chlorine is formed. And if that's what you're assuming, You're absolutely correct. All right, so chlorine gas would be formed. Yes, definitely. All right, how about this one? With reference to the previous question, at which electrode is the gas formed? So which electrode would that yellow-green gas or greenish-yellow gas be formed? All right, see some answers coming in
I'm
the chat.
saying A is the answer given.
Lots of A.
Yes.
Yes. A is correct. Yes, that's absolutely correct. All right. Yes. All right. So let's move on. So it's very simple. So now that we just looked at is a molten binary ionic salt. Binary just has two elements. And it's simple cation, simple anion. All right. So you only have one type of anion and one type of cation. So and anode, cation goes to cathode. You know what's going to be complicated if you have an aqueous solution from the substance that you're putting in the water, as well as water ionizes, like producing its own ions. All right. So this is a typical setup for electrolysis of a dilute solution, and I'll tell you why it's like this when we see a certain pattern. There's a reason why they set it up like that, and if you understand what's going on there, it's kind of set up to collect gases. Right? It assumes that you're going to produce gases. All right. So let's go. Now let's look at electrolysis of dilute.
Sir, just a sec. I think there are some comments that you were breaking up one at a time. So if you could just repeat that section.
This little part here.
Yes, you're breaking up for some reason.
Okay. All right. Okay. Yes. All right. Okay. Right. So just a while ago, what we're saying now, we're going to look at the situation where we are looking at to electrolyze aqueous solution. Right. It's very simple when we're looking at a molten ionic binary salt. Right. There's only one type of an ion, one type of cation. The anion goes to the anode, the cation goes to the cathode. Now, what happens when you're electrolyzing an aqueous solution? Right. You have ions due to the water, and you have ions due to the substance dissolved in the water. What happens there? How can we deal with that? All right, so that's what we're going to look at. So we're going to look at dilute hydrochloric acid. And let's think about it. What ions would be present in dilute hydrochloric acid? Write it in the chat. What are the ions present in dilute hydrochloric acid solution?
Okay, we have hydrogen ions H, there's OH, there's Cl, from what I'm seeing. There's H plus, somebody said chloride ions.
Yes.
Hydrogen and chlorine ions, H plus Cl minus, H plus OH minus.
Excellent. All right, so HCl itself is going to produce hydrogen ions and chloride ions, and water, all right, is going to produce hydrogen ions. Water hydrolyzes ionizes slightly. So I shouldn't be putting it like that, but hey, this is CXC. Don't get too worried, hung up about that. So we have hydrogen ions, all right? But we have two different types of cations, yeah? So in terms of what's going to happen at the cathode, the situation is very simple, all right? What's going to go towards the cathode? Cations, right? All right? And to the anode, going towards the anode, we have two competitors. We have Cl and OH minus. All right. Now, when those ions will be discharged? For now, for you, for now. What you need to learn is how to make that choice. All right, anybody knows how to make that choice? Anybody want to advise me? How do I choose which of these ions will be discharged?
Somebody says electrochemical series, ECS.
Yes, yes. Very good.
Okay, and when you get a chance, somebody was saying they didn't understand the second question from the Molten section.
Mm-hmm.
So when you get a chance to revisit.
Okay, the second question was with reference to the previous question, at which electrode was a gas formed? So the previous section where it said chlorine was formed, we said greenish yellow, yellowish green gas, which is chlorine. So from the electrolysis of iron 3 chloride, chlorine was formed. All right. So if we're electrolyzing iron 3 chloride, then we have iron 3 plus ions and chloride ions, which is Cl minus. All right. So the chloride Cl minus an anion, so that must have gone to the anode. All right. So the yellowish green gas, which is chlorine, must have been produced at the anode. That was our answer. All right. So yes, the electrochemical series. Yes, the electrochemical series. But there are other factors as well. So there are three factors affecting the discharge of ions at the electrode, determining which ion will be preferentially discharged at the electrode. There are three factors that we have to consider. The first one, the most important one, as far as you're concerned, is the position of the ion in what we call the electrochemical series. All right. There's also the concentration of the ions in the electrolyte, and there's a type of electrode. All right, so let's look at the electrochemical series first. So the electrochemical series is a listing of ions in order of how easily they become discharged at an electrode. All right, so the ones at the top are the most difficult to discharge, and the ones at the bottom are the easiest. All right, so potassium ions are difficult to discharge. All right, so potassium wants to remain in the ionic form, doesn't want to become atoms. All right, and yet you'll find generally the more reactive the metal, the higher it is in the electrochemical series. The two are almost the same. All right, there's a few little differences, but they are very, very similar, and for good reason that you might learn later if you do chemistry in 6-1. All right, so if you have zinc and potassium going to if you have zinc ions and potassium ions going to an electrode, going to the cathode, right? The zinc is going to be discharged instead of the potassium because the zinc is lower in the electrochemical series, right? Similarly, over the anion side, okay, you notice that sulfate is at the top, hydroxide is at the bottom. Now, make special note of this. Hydroxide is where? At the bottom. Easiest to discharge. And so all aqueous solutions are going to contain this hydroxide ion, yeah? So if you're only depending on the electrochemical series, hydroxide gets discharged at the anode every time, right? If the electrochemical series is the only factor that you're looking at. Of course, there are two other factors, we'll talk about them, right? So, for example, if your solution is dilute, that means concentration is not a factor. And if you're using inert electrode, hydroxide is going to be discharged every time. All right, and that's why you find that when you electrolyze dilute solutions, you tend to discharge hydroxide, producing oxygen at the anode. All right, so there you go. I just want you to note one other thing. All right, your hydrogen and your copper and silver. All right, these jewelry metals are easy to discharge. Yeah, the copper and your silver. All right, they are the least reactive. They're right down at the bottom. All right, so they're easy to discharge. All right, and the very reactive metals are hard to discharge. That's what it is. So you must remember, you must study this electrochemical series. You must know it. Okay, there's no way around that. You got to know it. All right, so generally speaking, then the lower the ion electrochemical series, the easier it is to discharge. All right, but if the ion is in high concentration, it will be preferentially discharged even if it is lower in the electrochemical series. All right, so if the concentration, so the electrolyte has a very high concentration, especially on the anion side, right? What will happen, there's a special one that is different from, it's not just a special one, but there's a special case that I'm going to talk about that goes against this. But especially on the anion side, high concentration means that electrolyte, that ion that is in higher concentration will tend to be preferentially discharged, even if it is lower in the electrochemical series. All right, inert electrodes like the one that we mentioned previously, graphite and platinum, right, do not take part in the reaction, right? There are only a couple of occasions where we use active electrodes, and we'll come across it in your syllabus. And that is when we're looking at the purification of metals or electroplating. All right, outside of that, we don't use active electrodes. All right. Okay, so we're dealing with HCl, remember, right? Dilute HCl. All right. Well, somebody wants to know the name of the channel, Dr. Campbell.
Yes, put it in the chat. Jamaica Teaching Council.
Okay,
Right.
so we're looking at the chat, folks. All right. Yes. All right, so we're looking at HCl. Okay, so at the cathode, we said that there's no charge, just hydrogen ions. That's straightforward. All right, two hydrogen ions combined with 2 moles of electrons, and you form a mole of hydrogen gas, H2. All right, pretty straightforward. Should be no problems with that. Right, so this is reduction. Right, reduction occurs at the cathode, oxidation occurs at the anode. All right, so reduction of hydrogen ions to produce hydrogen gas. All right, and everybody should know when you produce a gas inside a solution, you get bubbles or fizzing or effervescence is the official word. All right, all right. Look at that. Give me one moment, please.
Okay, so students, remember that the session is being streamed as we speak. It's on YouTube. If you just type in Chemistry Camp Day 4, you will find the link. All right. And of course, we will share the recording afterwards to the emails, to the email addresses. All right. So you will have access to the session.
All right, back again, folks. Sorry about that. All right, so at the anode, yes, you can see hydroxide ion. Folks, this half equation, you're just gonna have to swap it. All right, there's no easy way of telling you that, but it's just a reality. You have to know the half equation for the discharge of hydroxide ion to give you oxygen, 2 moles of water, and 4 electrons. So you have to study that one. All right. So particularly because this is what happens with most solutions, most dilute solutions, the hydroxide is going to be discharged. You're going to get oxygen, 2 moles of water, and 4 electrons. So, all right, we have to study that. So basically now we're knocking out hydroxide, we're knocking out hydrogen ions. So what's going on? Look at this picture. And they love to ask about the look of this picture. All right, so at the cathode, we're getting hydrogen. At the anode, we're getting oxygen. But you notice that the amount of hydrogen is about twice the volume of oxygen. You just look at it, all right? And this always happens when you are electrolyzing a dilute solution. Let me show you why. All right.
Someone is asking if you always get oxygen in a dilute solution. Right. Always get the OH being discharged, sorry.
Okay, right. If once the dilute solution at your level, yes. Once you're at a dilute solution, the hydroxide is at the bottom of the electrochemical series. That's going to be discharged. So you're always going to get oxygen at the anode. All right. So if we look at this, what's happening here? All right, we are knocking out hydrogen ions and we're knocking out hydroxide ions. All right. So we are removing water. All right. So once we're removing water, we're actually turning water into hydrogen at the produced at the cathode and oxygen produced at the anode. All right. So we are basically making this solution more concentrated. We still have HCl ions, but we have less water. All right. So we're making the solution more concentrated. So the solution will become progressively more concentrated over time. All right. This as the electrolysis continues. Now, the other thing I wanted to tell you about wanted to show you was why this volume is twice the volume of oxygen. Why the volume of hydrogen is twice the volume of oxygen. All right, so at the cathode, what happened was we had hydrogen ions. All right, let me use a different color. Let's get rid of this here. Let's use a different color. All right, let's get back to that. We had hydrogen ions. All right. Hydrogen ions gaining electrons and forming hydrogen gas. All right. So we go H plus E gives us H, but we know that hydrogen exists as H2, so we need 2 of that and 2 of that. But when the hydroxide ion is discharged, we need 4 of them being discharged to give us 2 water molecules, oxygen gas, and 4E. All right. Now, here's the thing now. When we set up a circuit, the number of electrons flowing through the anode will be the same as the number flowing through the cathode. All right. So although we write this like this, when 4 electrons are released into the anode here, 4 electrons actually reach the cathode. So if we take that into account, if we make this 4, if we make that 4 electrons here, then we're going to need 4H plus. And then that will produce 2 moles of hydrogen. All right? So if we're looking at this carefully now, we produce, every time 4 moles of electrons flow through the circuit, right? We get 2 moles of hydrogen, but only 1 mole of oxygen. Right? So we're producing 2 moles of hydrogen to 1 mole of oxygen every time 4 moles of electrons flow through the circuit. Okay? So that is why the volume of hydrogen is always twice. If you're electrolyzing a dilute solution, right? Then the hydrogen to oxygen ratio is going to be 2 to 1. All right? 2 to 1. Now,
okay, so there's a question. Someone is asking, if one does not remember the electrochemical series for the cations and anions, is it possible to use the periodic trend in electronegativity and electropositivity to answer any question related to displacement at the anode or cathode, respectively? That's a very long question.
That's a very long question. that takes some working out. That takes some working out. You have to be careful. You can think about I would say the next best thing you can do is think about the reactivity series. But try to remember the electrochemical series. Now, somebody asked a question before about if you always get a 2 to 1 ratio. Somebody asked a question, right?
I don't remember, but maybe.
Yeah. I think I need to explain that. There's one little, it's not one, but there's a little problem with it's not always. Let me tell you why it's not always. It's not always because, let me show you the little problem. Let me go back to the electrochemical series. If I go back to the electrochemical series, where is my electrochemical series? Up here. there. Right, one more. All right. Now, it's not exactly down the bottom. Right? So in the solution, these here. I'm always going to produce. I'm always going to produce hydrogen above. Are you guys back with me?
Sorry, we didn't hear you. Go again.
Okay, yeah, I realized that I dropped out. Right, so I'm saying that you always produce hydrogen for dilute solution. You seem to always produce hydrogen at the cathode, except for those solutions that have copper or silver. All right, so you have to remember that copper and silver are actually below hydrogen in electrochemical series. So if I'm electrolyzing copper sulfate solution using inert electrodes, for example, right, I'm not going to get hydrogen at the cathode because copper is below hydrogen. All right. So for the anion, you always the hydroxide will be always because hydroxide is at the absolute bottom. But at the cathode, you don't always get hydrogen gas, right, for a dilute solution. Right. You have to take into consideration the jewelry metals that are below hydrogen in the electrochemical series, because those would be discharged instead of hydrogen, okay, in dilute solutions. All right. So
someone was asking, I think they're saying you had a statement to say that the ones below the list can be preferentially displaced. Why is that so? It was on a slide with the 3 statements of anodes not taking place in a reaction. So there's a query on one of those statements. I think it's the one that mentions the factors or something.
You mean this one here?
Yeah, that one. Yeah.
And what was the question?
Why what the mention about the ones below the list can be preferentially displaced? Why is that so? I think it's the second statement about the concentration.
Okay. Mm-hmm. Oh, why? Okay, why is it so? All right. No, you want to go into. All right. So the electrochemical series. I don't want to go. I don't want to go into the cave stuff, but electrochemical series is actually based on. Oh boy, are you hearing me?
Yes, yes, we're hearing you. We're hearing you.
All right, electrochemical series is based on a concept called equilibrium. Actually, it's a measurement that kind of gives you an idea of how easy an ion, right, or a substance is able to gain electrons. An ion is able to gain electrons. All right, that's what it is. Okay, so there are different factors that affect equilibrium, and one of them is concentration. All right, so concentration does affect equilibrium, and it does affect the likelihood of an ion to gain an electron. Right, so that is why concentration is a factor. I would have to teach you equilibrium or equilibrium, chemical equilibrium, at least an introduction, to show you how the concentration affects it, and that would be clear to you. But that's not on your syllabus right now. So don't worry yourself about that. Just know that that is what has that's what you have to accept at this stage, right? But it's a good question because I'm going to show you an example that I would have to mention what you just asked me. So it's a good question. All right, but just accept that for the moment. All right, what was the question I was going to ask you next now? All right, what gas do you think will be found at the anode when aqueous copper sulfate is electrolyzed? All right. All right, and the answer is there already. I was to go slowly, but I went too fast there. Not sulfur dioxide, but oxygen, because again, sulfate and hydroxide would be at at the anode, would be going towards the anode, and then the hydroxide ion would be preferentially discharged because it is below the sulfate in the electrochemical series. And that would mean that you get oxygen gas, all right? And at the cathode, you'd get copper metal because copper is below hydrogen in the electrochemical series, all right? All right, so just to summarize, negative ions from the electrolyte are discharged if they are chloride, bromide, or iodide ions. For sulfates and nitrates, oxygen from water is discharged. This is for sorry about that. This is a kind of summary, all right, for what we just done. I don't want to let me skip that. Let me skip that for the moment. I don't want to confuse you with what we just did. I think what we did was just
will you be explaining the concentration effect, or you will take that on in a little while?
I'll take that on in a little while. I'll take that on in a little while.
All right, no problem.
I'll take that on in a little while. All right, try this one. During electrolysis of sulfuric acid, hydrogen gas and another gas are produced. What is the other gas? All right, anybody wants to try that one? Quick in the chat. During electrolysis of sulfuric acid, hydrogen gas is produced, as well as another gas. What is the other gas? What do we see? Oxygen. Yes, hydroxide is discharged because hydroxide and sulfate would be at the anode, and the hydroxide is discharged preferentially because it is much lower in the electrochemical series. All right, let's talk about applications of electrolysis. And one of those key applications is electroplating. Electroplating is important because sometimes we coat an object with a certain type of metal for different reasons. One of the reasons we do that is because we're trying to prevent corrosion, for example, or we're trying to give the object a certain properties that we want it to have. All right, and so we coat it with another metal. And when you're doing electroplating, it's very, very simple. All right, just remember this. Whether you're purifying a metal, all right, or you're doing electroplating, here's one thing you have to remember. All right, right? What do you have as the anode? What do you have as the cathode? The cathode is the object to be coated. Write that down. The cathode is always the object to be coated. So here I'm trying to coat the spoon. All right? All right? What am I coating it with? Whatever is over at the anode. Right? And in this case, I'm trying to coat the spoon with silver. All right? So I make silver the anode. See the silver is connected to the positive terminal. See the spoon, the negative. All right? And then the other thing that I have to remember now is what should be the electrolyte. The electrolyte should be a soluble salt of the metal that you're coating with. So in this case, I'm coating the spoon with silver. So the electrolyte needs to be a silver salt, aqueous silver salt. All right? So silver nitrate, and nitrate, of course, nitrate is a popular choice of an ion because all nitrates are soluble. Right. So again, quick summary, right? Whether we're doing electroplating or purification of metal, right? Here's what we need. We need the object to be coated or plated at the cathode. We need at the anode the metal that we are coating with. And we need as the electrolyte, right, a solution of the metal that we are coating with, a soluble salt, metal that we're coating with. Simple? Yes, no. All right. There you go. All right. All right. So these things, okay. All right. So I'm going to stop there. I'm going to stop there for the qualitative section. I'm going to switch over now to the quantitative electrolysis, and then we'll start with the question. So I'm gonna skip over here. Okay, good. All right, so I'm gonna do a new share. All right, so I'm gonna go here, present. All right. Now, the quantitative section of electrolysis has to do with the relationship between the amount of electricity that passes through the circuit and the quantity of product formed at the electrode. So there's a relationship between the amount of substance discharged or produced at an electrode and the amount of electricity that flows through it. All right? In fact, it's a proportional relationship. All right? And though that relationship is described by Faraday's laws of electrolysis. All right? And I'm sure that most of you know them or you have come across them already. And here I have summarized the two laws of electrolysis. The first law, right, which is very important. One says that the amount of substance discharged at an electrode during electrolysis is directly proportional to the quantity of electricity passing through it. All right? And there you have, your equation for the quantity of electricity. Q is equal to IT. All right. So you have two different units for the quantity of electricity. You have what we call coulombs. So when you multiply current in amperes and the time in seconds, your unit for the quantity of electricity there is coulombs. All right. And the other unit for quantity of electricity is the Faraday. All right, where 1 Faraday is equal to 96,500 coulombs. They'll typically give you this constant, but it's useful to just know it yourself. But if they give you if they round it off, use whatever value they give you, okay? But they typically give you it on the examination paper. But still, you want to know it for yourself before. All right? Am I off?
Your screen went.
A screen went. Okay. I think it's just about this.
Somebody was asking to repeat the statement about electroplating.
All right. So for the electroplating, all right, you need at your cathode, you need the object to be coated. So if I'm coating a spoon, I need my spoon at the cathode, connected to the cathode. Yeah. And then for the anode, I need the metal that I'm coating with. So if I'm coating the spoon with silver, I need the silver, pure silver metal as my anode. And then for the electrolyte, I need a silver salt. All right. Yes. All right. So Q equal IT, that's your quantity of electricity. And then for the second law, right? Second law relates the Faraday to the size of the charge, size of the charge on the ion that is discharged. Okay, so it says here, as you can read it, says there that the number of Faradays to discharge 1 mole of an ion at an electrode is equal to the size of the charge on the ion. So if you have Mg2 plus, you're going to need 2 electrons, 2 moles of electrons. So if you have 1 mole of Mg2 plus, you need 2 moles of electrons, and that will give you 1 mole of magnesium. All right. All right. And 1 Faraday flows when 1 mole of electrons flow for 1 second. All right. So that's for the physics people will know that. So if we look at this, when each mole of electron represents 1 Faraday. So the fact that 2 moles of electrons are in this half equation, that's telling you that 2 Faradays of electricity are required to discharge 1 mole of Mg2 plus to give you 1 mole of magnesium. Of course, 1 mole of magnesium weighs 24 grams. 2 Faradays produce 1 mole of magnesium. All right. All right, quickly in the chat. How many Faradays of electricity are required to produce 2 moles of magnesium? Given that Aluminium 3 plus 3E gives us Al. Talk to me. Write in the chat. How many Faradays of electricity are required to produce 2 moles of magnesium, of aluminium metal?
Okay,
All
so I'm
right.
seeing
What
2
are
and
we seeing in the chat
3s, a
there?
few 3s. 3, 3.
Mm, mm, yes. Let's have patience.
You
Let's go
waiting?
again.
Okay, I see
So
a
keep
6.
going, folks. Keep writing your answers in
I
the
see
chat.
a few 6s. 6. 6 with a question sign.
6 is beginning to appear now.
Yes,
Yes.
6 is coming on.
Janelle,
Okay,
good job.
so I'm seeing 6.
Good
Yes.
job. Yes. All right. So the people who see 6 have read the question well. Right? The people who are writing 3, you did not read the question at first. You didn't read it properly. All right. So you have to be focused. It says, how many are required to produce 2 moles of aluminum? All right. And we can see that from this, we can see that 3 Faradays. We can see that 3 Faradays. All right. Let's write it out. Let's just do it out so that everybody can see how we got that answer. All right. So 3 moles of electrons, so that's 3 Faradays, and that produced 1 mole of aluminium. So if we have 2 moles of aluminium, right, 3F produces 1 mole, so 2 mole. Yeah? If we double the number of moles, then we would have to double the number of Faradays, no? So that's X will be equal to 6. Right? Good? 6 Faradays. All right, good. All right, so back, back to plan. All right, good. Another one. Another one. Think carefully about this one now. How many Faradays of electricity are required to produce 2.3 grams of sodium? 2.3 grams of sodium. How many Faradays are required to produce 2.3 grams of sodium?
Okay, so I'm seeing 2.3. That's the first answer. 0.1. Okay, 0.1. Yeah, a few 0.1s.
All right, we're getting some 0.1s. Here we go,
Yes.
Tiana.
Yes,
All
well,
right.
that's 0.1. Yes, go ahead. Yes.
All right, so people are getting 0.1. All right, so don't get mixed up with the units now. See a few people who are quick on the draw got mixed up with the units. So this is sodium, all right, Na plus E minus gives us Na. So that's 1 Faraday, that's 1 mole of electron, and that's producing 1 mole of sodium, which we know is 23 grams. The molar mass of sodium is 23. So if we have 2.3 grams, how much, how many Faradays would that be? You can see that from 23 to 2.3, you divide it by 10, right? See that? Surely you can see that. We just move the decimal place 1 place to the left. So we divide it by 10. So we just divide 1 by 10, right? X equals 2.3 times 1 over 23, which is equal to 0.1, right? Faraday. All right? Straightforward, I should think. But make sure you don't rush into your answer. Sometimes you're so confident, you rush into your answer, you don't think about it carefully. You can get burned like that. All right? So be careful. All right, last one for this one. How many Faradays of electricity are required to produce 12 decimeter cube of chlorine at RTP. 12 decimeter cube of chlorine at RTP. How many Faradays do we need to produce 12 decimeter cube of, how many Faradays, required to produce 12 dm cube of chlorine at RTP?
No responses yet. Somebody wants you to go back when you're finished so they can see something. Okay, I'm seeing one answer, one.
One. RZTLK, you've been doing well. You're doing well, but did you get this one right?
So I've seen a few ones.
Few ones.
Uh-huh.
All right. Yes. More ones.
Yes.
Yes, yes, yes. All right. So if we look at this carefully, this is 2 Faradays. This is 2 moles of electron for 1 mole. Eh? All right. So let's look at it. All right. So we clear this. All right. Cl 2 Cl minus is just Cl2 plus 2E. This is 2 Faradays. Okay. And that is 1 mole of chlorine. 1 mole of chlorine is the same thing as 24 decimeter cube at RTP. Because we know that 1 mole of any gas occupies 24 dm cube. We have 12 decimeter cube being produced, then that must be, you can see that half of 24 is 12, eh? 12 is half of 24. So all you have to do is half 2 Faradays, 2. Whatever you do to this side, you do to the right hand side. Yeah? Yes? Simple math. It's supposed to be. All right? 12 times 2 over 24. All right? And that is 1. Okay? Faraday. All right. So very good. RARTLZK. I can't remember all of those letters. Very good. You did well. All right. So let's go back now. All right. Let me see. All right. So I have a few summary multiple choice. Maybe I'll come back to that later. What I'll do is that I'll go to some questions. All right, that are some of the type that you might see on your exam. So let's start with this one. All right, so make sure, I hope you can see that diagram there. Let's look at the diagram. It says the diagram shows the electrolysis.
Not seeing the diagram.
Molten. Not seeing the diagram? All right, let me stop share. Try a new share. All right, it means that it's getting okay.
Okay,
there now?
seeing it now. Yes, yes.
All right, good. Good. All right, so here we go. Yes. So it says here that the diagram shows the electrolysis of molten lithium bromide. Molten lithium bromide. All right. And you have the diagram labeled, and the first question says, write an ionic equation for the reaction at the negative electrode. The negative electrode. All right, so go ahead and put your answers in the chat. Write an equation for the reaction at the negative electrode.
No responses yet.
Negative electrode, talk to me.
Okay, so here we go. Somebody has 2
All
Br
right,
minus. Somebody has 2 Br minus plus 2 electrons.
Balance.
Br2. Okay, somebody else has 2H plus two electrons to give you H2. Lithium plus electron give you LiS. Lithium solid.
All right, so think carefully now. Think carefully now. All right, this is lithium bromide. All right, lithium bromide. I saw somebody have, what has what? Li, was it Li plus E?
Yes.
All
So
right.
one person has it in aqueous state, another person has it in liquid state.
All right. All right. So look, read the question carefully. It's lithium bromide, molten lithium bromide. Okay, folks? All right. Pay attention to the electrolyte. Molten essentially means melted. That's right. In a liquid state. All right. So there are no aqueous ions. It is just LiBr. Okay. That's it. LiBr. This is a binary ionic salt, just two elements, right? So lithium bromide will give you lithium ions, that's Li plus, because it's in group 1, and Br minus ions, that's in group 7. All right? So the lithium would be going to the cathode, eh? The cations go to the cathode, right? So at the cathode, right, the lithium ion, which is Li plus, right, will gain electrons, right, to form lithium metal, right, and it will be liquid state, all right? Write the ionic equation for the reaction at the positive anode. Let's see if people are getting at the positive anode. No, people are getting positive anodes. All right. So Christine, watch your state symbols there. All right, they'll be all liquid. Okay, not aqueous. Those aqueous will be getting very different products. All right. So anybody?
No responses yet.
For the,
no responses yet for the for the anode.
For the anode, talk to me. Notice that one is 2 marks. There must be something special about that one. That was not so special about the first one. One is 2 marks.
Not as simple. All right, somebody has Br liquid plus to give Br liquid plus electrons. Somebody else has 2 Br minus to give Br2 plus 2 electrons.
All right.
Yes, and somebody has 2 Br minus plus 2 electrons to give Br2. You could probably point out how you write the equation for the electrons to cancel. I mean balance.
All right. So the bromide, remember now, the bromide is going to go towards the anode, eh? And what they do, the anions, what anions do is that they give up electrons, right? So they give up electrons. Now, that means that they're going to give up electrons. So you could almost just do this. It's going to give up electrons. And you can look at the charge and see how many electrons you're going to give up. So that's Br minus gives you 1 electron plus Br. So you could do that initially, but you know that bromine exists as a diatomic molecule, right? So you're going to form bromine molecule. So that means you need 2 of these. And if 1 give up 1 electron, then 2 would give up 2 electrons, right? So
can you repeat that? You were breaking up.
Anions give up electrons, right? The cations gain electrons. So you add electrons to the cations.
Sorry, you're breaking, so you might have to repeat that entire section.
Everybody got that?
Sir,
Am I buffering again?
you were yes. So could you just repeat the entire bromine thing?
Are you hearing
The
me?
entire explanation. We weren't hearing you clearly.
Yeah, I realize. Okay, you hear me again?
Yes. So you can just go over that explanation.
All right, so let me go back right there. All right, so what I'm saying, folks, is that, are you hearing me now? You hearing me?
Yes.
Yeah, good. So I'm saying that, okay, yeah. So if we think about what is going on, right? So as you think about what is going on at the anode, bromide ions going to the anode, eh? And anions, like bromide, they give up electrons. So they give up electrons. So you could start by just writing anion goes to E. And then you look at the charge here and adjust the number of electrons. Okay? So I have, give me a second, let me just make a little adjustment. Right? So if we look at it here, right? Br minus, because it's just one negative charge, is going to give up one electron. Okay? And of course, you form now a neutral bromine. But we know that bromine exists as Br2 molecules. Okay? So that means that we need two bromide ions to make that Br2. And each bromide gives up one electron. So if I have two bromides, I can give up two electrons. All right? So that's an easy way to remember how to write the half equations. Cations, you add electrons to cations. Anions give up electrons. Okay? All right. Which ion is oxidized? Explain your answer. All right, in the chat, which ion is oxidized? Quickly. Brianna says lithium. Siobhan says lithium. Okay, Hoyla or Johnson says lithium. Oxidized. Janelle says bromine. Seal says bromine. I have the bromines are coming in late here, Dr. Campbell. Bromine. All right, give me your explanation because it'll be interesting because we have some split answers.
So they're given bromine. Somebody says bromine because it has lost electrons. It loses its electrons. At the anode, oxidation takes place. Oxidation is losing. Bromine is being oxidized because it is losing electrons to turn from bromine ions to bromine gas.
All right. So that means we need to brush up on our definitions for
oxidation and reduction. Yes.
All right. Yes. Let's talk about it. Oxidation is increase in oxidation number, loss of electrons, addition of oxygen, or loss of hydrogen. All right. At this stage, we're focusing on the oxidation number and the loss of the electrons. Right. So oxidation is increase in oxidation state or number, or loss of electrons. And you're right, bromine people, bromine clearly loses electrons, right? So each bromide ion, loses one electron, okay? Each bromide ion loses one electron. So bromine is oxidized. You could also look at the oxidation number, right? Oxidation number of bromide is the same as the charge on the ion, which is -1, and that increases to 0 for bromine, all right? So, yes. Mr. Thompson?
There's a raise, yes. I'm going to it. Where is he? I'm not seeing his hand again. Thompson. Is he still raising hand?
I don't see it. I don't
it's
see
gone.
it.
It's gone. All right.
Oh, all right. Okay. All right. So let's go. Determine the mass of product produced at the cathode, given that a current of 20 amperes flowed through the circuit for 20 minutes. All right. Now, okay. All right. Interesting. So you're gonna have a go at this one. All right. So I'm gonna give you a couple minutes and you have a go at this one. All right. And then we will discuss it. I'm going to give you a couple
Sir,
minutes.
yes, while you're waiting on them, there were some persons wanted to, yeah, so there's still some explanation needed for how you know the oxidation based on the oxidation number changing, right? So that is one. Somebody's asking though, so the statement was, so let me get something straight. Generally, cations give up electrons, but anions take them. However, in electrolysis, cathodes take, but anodes give. I think you probably just need to explain clearly what's happening there, because I think they're a little confused a bit.
All right. So let's go again. Let's go again. All right. So let's start at the beginning. So in electrolysis, anions go to the anode. Anions travel to the anode. All right. Are we clear? So in electrolysis, anions travel to the anode, where they give up electrons. They give up electrons. So anions give up electrons. All right. And then cations travel to the cathode. Where? Are we clear? Cations travel to the cathode where they gain electrons. So in electrolysis, cations gain electrons, become discharged, and anions lose electrons to become discharged. Think about it. Cations, they are positive, so they're lacking electrons. Anions are negative, they don't have too much. Right? Think about it that way. They have too much. So they have an excess. They'll give up the excess. All right? Think about it like that. All right, I see some answers coming through. I see 1.49, I see 1.75 grams.
Yes, there's a 1.74. Somebody wanted to know why it's not the lithium that was oxidized.
All right, so lithium, if we look at lithium, let's look at lithium. Lithium plus, let's got it there, gains an electron. All right, reduction is gain. All right, if you gain an electron, you are reduced. All right, so yes, so gain of electron is reduction. So lithium is reduced. You can also look at oxidation number. Oxidation number of lithium decreases from +1, right here, to 0. Right? So this is a positive ion. So the charge on the ion is the same as the oxidation number. It's a simple ion. So lithium plus has an oxidation number of +1. And lithium by itself, the element by itself, in its free state, has an oxidation state of 0. So literally, oxidation number has decreased from 1 to 0. So again, on that count, we're dealing with reduction. All right, so we're getting some more 1.7s now. All right, so let's see if we can work that out. All right, so first thing we need to work out is use the first law to get the quantity of electricity flowing, and that's Q. The quantity of electricity is IT. So we got 20 amps, right, as a current, and the time has to be in seconds, no? So 20 amperes, we have 20 minutes to convert 20 minutes to a second, you have to multiply by 60. All right, so if you do that, you're getting 24, talk to me, 24,000 coulombs. Yes, everybody got that?
Could you repeat? You were breaking up.
Plus
Could you repeat the sir? Could you repeat the calculation part? The Q is equal to IT part.
Yes, man. I'm gonna go all over it. All right. All right, so let's go. So the first thing we need to do is to get the quantity of electricity. All right. And the quantity of electricity, remember that from the first law, Q is IT, and Q being the quantity of electricity, I being the current in amps, T being the time in seconds. So the time is 20 minutes, so we need to convert 20 minutes to seconds. So you multiply by 60. That's 20 times 60, so that's 1200 seconds times the current, which is 20. So you get 24,000 coulombs. All right. Now we need to look at the equation for this charge to figure out what's the relationship between the quantity of electricity, the charge, and the quantity of substance formed. All right, so lithium, all right, so 1 mole of lithium is formed here. All right, 1 mole of lithium, if you look at your periodic table, lithium is as relative atomic mass of 7. So that's, it's going to be 1 mole or 7 grams. 1 mole of lithium is going to weigh 7 grams. All right, and this is, of course, charge. All right, so 1 Faraday, all right, is the same thing as 96,500 coulombs. All right, and that produces 1 mole or 7 grams of lithium. All right, you produce in your reaction here 24,000, right, coulombs. All right, so if we run 24,000 coulombs through, we can find out how much lithium would have been produced. All right, so X, the amount of lithium, right, would be 24,000 times 7, all right, over 96,500. All right, and people who do that are getting what?
Well, the answers in the chat were the 1.74 and I think 1.79. And
yes, people are getting 1.74, depending on how much rounding off you do.
right.
I've not done much rounding off there. You should be getting 1.74 grams.
How do you know it
Of
is
course,
7 grams? How do you know it is 7 grams? I think it's related to the lithium.
All right, so in lithium, right, so you'll be given the molar mass of lithium, right? So that I didn't show you that there, but you would be given that. All right. So don't worry about that. All right. Good. So let's just give you a minute to absorb that. If you have any questions, type it in the chat. All right. Molar 7 grams, the molar mass of lithium. All right. So remember, I wrote the relative atomic mass for lithium up here, 7. The molar mass is the same number in grams per mole.
Question, how do you get the 96? I guess it's the
96,500. That's a constant that you're normally given, right? That's a conversion from Faraday's to Coulomb. Normally you're given that in the question, but you could it's something that you should remember really. All right. So it's two different units of charge. Okay, it's just a conversion.
If you could just repeat why you have a 7, that's 1. And number 2, somebody's still saying they don't understand why bromine is oxidized.
All right, continuing. I think everybody should have I've gotten a chance to look at that. As lithium bromide is electrolyzed, a colorless gas is formed at the negative electrode. Now look at this carefully now. When aqueous lithium bromide is electrolyzed, a colorless gas is formed at the negative electrode, and the solution becomes alkaline. Explain these observations and include an equation in your answer. All right, so I'm going to give you a second to think about that. All right, you can answer in parts or the whole thing in the chat. Any part of it you want to answer. All right, you want to tell me what the gas is. You want to give me the equation. All right, explain why this solution becomes alkaline, what's going on, what's happening in this electrolysis. Aqueous lithium bromide. All right, somebody says bromine gas. RTLK is saying 4OH minus goes to 2H2, O plus O2 plus 4A. Somebody said hydrogen is given off. Interesting one.
Not seen anything else?
All right. All right. No. So hear me now. Hear me now. Watch me now and watch me carefully. OH is given off. Yes, H2 for real. Water is given off. How can I get the recording? All right.
I give it. All right.
All right. So let's look at it. So remember now, remember this is a different part of the question. It says aqueous lithium bromide. So this is lithium bromide, aqueous, meaning that it is dissolved in water. Are you listening to me? This is lithium bromide dissolved in water. So this is a situation where we actually have lithium ions. We have bromide ions, but we also have water, which means that we have hydrogen ions and hydroxide ions. So now we have going to the cathode 2 cations, and we have going to the anode 2 anions. So we have to be able to choose what is going to be discharged at the cathode, what's going to be discharged at the anode. Talk to me. Hydrogen or lithium? Now, I know lithium takes you a little bit out of your comfort zone, right? But think about lithium in relationship to the other metals that are next to it. Which is going to be discharged? All right, I see some hydrogen is going to be discharged. I see a lithium. All right. Think about it. Lithium is a group 1 metal. The group 1 metals are reactive, right? That's it. Lithium is at the top of group 1, and as it's going to be higher in electrochemicals, cover all things. Okay, it just covers the ones that are on your syllabus. Okay, so this lithium one here now takes a little bit out of your comfort zone, but you have to be able to react. All right, because you might get one that you didn't plan for on your exam. And here's where you have to think about your chemistry. All right, so lithium in group 1, so you know that's a reactive metal. It's likely high in electrochemical series. The only metals that are below hydrogen, remember that, in your electrochemical series are the jewelry ones: the copper, gold, silver, platinum. Okay? Okay, folks? All the other metals are above hydrogen. So the hydrogen is going to be discharged. All right? The hydrogen is going to be discharged here. All right? So we're going to take out the hydrogen. That's going to be discharged. Okay? What about the anode? At the anode, what are we going to lose?
So you're saying OH minus?
OH minus. All right, I have to admit that I gave you a little problem here. I gave you a little problem. I should have said concentrated. You see, this is where I should have dealt with a little problem. But I'm gonna, there's another question that I'm gonna deal with the problem later. You should have said concentrated. No, hold on, no, man.
No, man, it doesn't affect there.
No,
It doesn't
that's
affect
not the
there.
wrong. I'm sorry, that's not the one. That's not the one. That's not the one.
It's a different one, yeah.
Yes. That's not the one. Okay. All right. I wonder if I had the. I put up a question. I wonder if I had the right thing for the next one.
Yes,
All
man.
right. So yeah. So colorless gas. So colorless gas is saying what at the anode? Sorry, my bad. I'm thinking different. Colorless gas is formed at the negative electron. So talk to me. What's going on there?
Right. So I think that well, somebody said hydrogen is formed at the cathode. Lithium goes to the cathode. Oh, they're answering another question. Right. So they're saying hydrogen is formed at the cathode.
Mm-hmm.
Positive ions are discharged at the cathode. Somebody has oxygen question sign. Yeah.
Mm-hmm. All right, good. All right, so yeah, so the hydrogen is discharged at the cathode. So we're gonna have 2H plus, all right, plus 2E gives us hydrogen. All right, good. All right, and it says the solution becomes alkaline. Now, if the solution is becoming alkaline, what's happening? We're losing hydrogen, right? And what are we leaving in there? We're leaving in lithium, bromide, OH. What's going to happen at the anode? If the solution is becoming alkaline, what does that tell you? What do you suppose I ask you? What gas is produced at the anode? What would you tell me?
Okay, so I'm seeing bromine is forming at the anode, and somebody has it is losing H plus ions. Br.
It probably means that bromine is forming at the anode, yeah? Because in the solution, you're being left with, if the solution is becoming alkaline, it must mean that you're being left with lithium hydroxide in the solution.
Well, I guess bromine, you need the concentrated thing there.
Yeah, man, it was the one. It was the one.
Right.
I was thinking, yeah, it does need to be concentrated. This is the one. I left off the concentrated. Yeah. So the bromine has to be discharged at the anode, right? And so that would be, so you would actually see reddish brown gas at the anode. Yeah, so that is it. I knew there was something there. All right, so we can go on. Let's do an application question. Application of electrolysis. This one is talking about electroplating. It says electroplating steel objects with silver involves a 3-step process. The coating of copper is applied to the object. A coating of nickel is applied to the object. The coating of silver is applied to the object. The diagram apparatus for the first step is shown below. All right. Let me see, make sure that you can see this one. Yes. So there's the diagram. This is very nice. Sometimes they'll ask you to draw the diagram, so you must be able to draw the diagram. That's why I told you those 3 important things earlier. All right, so don't expect them to always give you a diagram. All right, you have to be able to draw this diagram, right, to show what happens during electroplating. But anyways, this one is easier, on the easier side. At least that's the idea anyway. Okay, so let's look at it. Electroplating steel objects with silver involves that process, 2-step, and they're giving you the diagram for the first step. So think about the first step. It says the chemical process taking place at the surface of the object is this. Explain whether this process is oxidation or reduction. Some change, man. We just did it a while ago. Yes, what are you saying in the chat?
Okay, I see one answer, reduction.
Because there's an explanation, you know.
Oh, there's no explanation yet. Reduction.
Yeah, reduction because
somebody says gain in electrons, oxidation state is decreased. Reduction equal gain of electrons, gain of electron.
Right. So you get
went from 2 to 0.
Yeah. Oxidation state.
Because it is gaining electron. Yeah, yes. Gains.
All right. So oxidation state, you can use that as well. You can use the obvious, which is gain of electrons. So copper 2+ gains 2 electrons, right? So that is reduction. Explain why the concentration of copper ions in the electrolyte remains constant throughout step 1. Explain why the concentration of copper ions in the electrolyte remains constant throughout step 1. Let's go to one now. Let's see how many you can get this one. Why is the concentration going to remain constant? Let's see what you can write for that one.
Okay, sir, could you write the answer as close to the question or on the line as possible?
Yeah,
I think somebody wants to. All right. So somebody's asking about, let's see.
So copper 2+ gains 2 electrons.
Right.
All right, so for this one, all right, because silver cannot replace copper from the anode, replaces copper in the electrolyte. Okay, as you're in there as usual. Electrolyte contains copper, so as to reduce, it is reducing, it is being put back into the solution. All right. So yes, so the concentration of copper 2+ ions in the electrolyte remains constant, because for each copper ion, right, for each copper ion that deposits on the steel object, a copper ion is placed into the solution from the anode, right? So a copper ion, for each copper ion that is deposited on the cathode, 1 copper ion from the anode goes into solution, right? So yes, so as soon as you lose 1 from the solution, 1 from the anode replaces it in the solution, right? And so there's no loss, there's no net change in the concentration of copper 2+ ions in the electrolyte. All right, all right. So for each, let me try and write it. For each electron depositing, I'm using a mouse, people, so it's not so easy.
Recording
on the cathode. Right, from the solution, enters the solution from the anode. All right. Yes. So for each electron depositing on the cathode from the solution, a copper 2 plus ion enters the solution from, all right, let's get two in step 2, right? So what are the 2 changes I would do to this to coat the object with nickel? What are the 2 changes? Talk to me. What are the 2 changes I would need to effect in order to do a coating of nickel? In the chat, talk to me.
All right, I'm not seeing anything yet, but somebody's asking about the difference between active and inert electrodes when you have a chance.
Okay.
All right, so the answer is coming. Change electrolyte and anode to nickel. Nickel goes to anode. Change electrolyte. Well, they're not giving me an electrolyte yet. Use a nickel anode.
Yes. Yes, so we change the copper to nickel. All right. The anode. And what else would we change?
They're saying use nickel nitrate electrolyte and use nickel anode.
All right, so we could use nickel nitrate or nickel sulfate. Right?
Nickel solution as electrolyte.
All right, yes, yes. Yes. Those are the 2 changes. Good, good. Good job. All right, so somebody was asking about active electrode. Somebody was saying, let me just answer the question about active electrode right here. Because it's exactly the situation we're talking about. Active electrodes. In active electrodes, it simply means electrodes that take part in the reaction. And electroplating is a use of active electrodes, right? So when we're doing purification of metals or doing electroplating, those are examples of using active electrodes. What's happening here? The copper, the electrode itself dissolves in solution. The copper anode dissolves into the solution. And actually those ions go over and deposit on the steel cathode, which means that the cathode is also taking part because it's changing as well. All right? So this is an example where you have an active electrode. The electrodes actually change their nature as the reaction goes on. All right? So this is an example of an active electrode. And then the inactive or inert electrode is like graphite and platinum. They don't change. They don't take part in the reaction. The reaction takes part in the electrolyte, right? And that's where the change occurs, and they stay the same. Okay? Yes, you were asking another question, Dr. Cameron.
Yes. Oh dear, if I can find it. Okay, so somebody wanted to know. Oh yeah, you were just answering that. About the active and the inert. I can't find the other one. All right. Yeah, that was it. That was it.
Okay.
I think you can, if you can just go over that part about why you would change if you were using, if you're coating with nickel.
Right.
Repeat the part about the active and the inert.
Remember now what we said, we're doing electroplating. All right, so yeah, so the active and inert electrode. All right, let me just make sure that you're hearing me. Oops, are you hearing me?
Yes, no, okay. You were muffled a bit before.
Okay. All right, so let me go again. All right, so what we're saying is that active electrode is when the electrode actually takes part in the reaction, just like in the case that we're looking at now in electroplating, right? Or in purification of copper, for example, right? Because what is happening here is that the copper anode actually dissolves in solution. It's decreasing in size as this reaction goes on. The steel object over here the copper anode is decreasing in size. The steel object is increasing in size. The nature of them is changing. The solution is not changing. That's not reacting, right? It's actually the electrodes that are reacting, right? So this is an example of a situation where we have active electrodes. And inactive electrodes now, or inert electrodes that do not take part in the reaction, those are, for example, graphite and platinum, right? When you use inactive electrodes or inert electrodes, all right, the reaction takes place in the electrolyte. The electrolyte changes, right? But the electrodes remain the same, right? And here where you have active electrodes, the electrodes are actually changing. The electrolyte remains the same. All right, so that's what's different. Okay, now in this case now, somebody said, why would we use nickel? Why do we use nickel sulfate? All right, remember what we said, that if you're doing electroplating, three things. First thing, the object to be plated or the object to be coated needs to be the cathode. Okay? And then the other two things, the object that you're plating with, the coating that you're applying should be the anode. All right, so we're applying nickel, so that anode should now become nickel. All right, and then the solution should be a soluble salt of the metal that you're coating with. I'm coating with nickel. I need a soluble salt of nickel, nickel sulfate or nickel nitrate if you don't want to take a chance. You know that all nitrates are soluble. Okay. Okay, final part of the question. Copper, nickel, and silver are transition metals. Oh, no, this is beyond you. All right, let's go to another. All right, so here are some questions from some actual CXC past papers here now. Here's, I think, simple one. Let's go with this one. Are you seeing it? May, June 28, 2008. You see that? Yes, I think you're seeing that. Are you hearing me?
Yes, yes.
All right, so let's look at this one. It says barium is below calcium in the same group of the periodic table. Draw a fully labeled diagram of the apparatus that could be used in the electrolysis of molten barium bromide. You should indicate the material from which the electrodes are made. All right, so I tell you, you have to be able to draw that electrolytic circuit. All right, so this would be similar to what we looked at first. All right, let me see if I can sketch it, and this is just a sketch, folks. All right, so you would need to have some container, probably made of ceramic material, very high melting point. All right, and you would definitely need to heat. Wow, I'm not drawing the Bunsen flame so good here, but yeah, you get the picture, right? You need to apply heat. All right, and you need your two electrodes. All right, you need your electricity supply. All right. Something like this. What would be your electrolyte? Would be that molten. You have to be able to do basic labeling, molten barium bromide. All right. What would be your electrodes? You use something like graphite, inert electrode. All right, they say that you are to label your electrode, graphite. Which one is the anode? Which one is the cathode? Is it towards the left or right? The positive end, the longer end. So this is your anode. All right, and this is your cathode. So you have to be able to do something basic like this. All right, there you go, something basic. All right, because it's a molten ionic salt, you have to heat it to keep it in a liquid state. I suspect you'd probably get the 3 marks even if you didn't put the heating part, because I think they're looking for the electrodes and the molten barium bromide. All right, there you go. All right, then it says write equations to indicate the chemical reactions that occur at the electrodes. So talk to me now. What would go on at the cathode? What's going to the cathode? What
So
ions
there
are present?
is Ba2 plus 2 electrons to give barium.
Yes.
Somebody's asking why graphite?
All right. Some people are joining the meeting late.
Yes.
So graphite, because graphite is an inert electrode. All right, it can withstand lots of heat. Yes. So barium plus 2E, barium 2 plus 2E gives you barium, yes, because your cation is Ba2 plus would go to the cathode, and then at the anode, right? Remember, this is a molten salt, so we only have 2 ions, 1 cation, 1 anion. So the bromide ions, right, would give up electrons. So we know that they're going to give up electrons. All right, but we know that bromine is going to form bromine, which exists as Br2. So we need 2 bromide ions, and each bromide giving up 1 electron. So we're going to get 2 electrons here. All right, so those are your reactions. It's liquid now, remember. All right, liquid. Later, the bromine would solidify, but this would be liquid here. And then bromine at those temperatures will be a gas initially. All right, talk to me. All right, so that's where you should be. And then, everybody okay with that? Let's go down to the mathematical part. It says a current of 5 amperes is passed for 2 minutes through molten barium bromide. Calculate the mass of the product that will be formed at the cathode. It gives you relative atomic mass of barium and bromine. All right. So the cathode, we know that that's going to be barium forming. All right. So let's look at that. All right. So we can start by finding out the quantity of electricity flowing through. All right. So the quantity of electricity flowing through is I times T. All right. So that's 5 amperes flowing for 2 minutes, but we must convert 2 minutes to seconds. So we have to multiply by 60. So that's going to give me, somebody calculate with me, 600 coulombs. Yeah. So there we go. 600 coulombs. All right. So that's the quantity of electricity that flowed. Remember what they said? 1 Faraday is 96,500 coulombs. All right, now let's talk about what happens at the cathode. At the cathode, we know that barium ions are going to gain electrons to form barium. All right, so that's 2 electrons or 2 Faradays to produce 1 mole of barium. All right. Now the question asks what mass. So we need the mass of barium. And we're given the relative atomic mass of barium, which is 137. We know that the relative atomic mass is the same number as the molar mass. So 2 Faradays is going to produce 1 mole, right? Or 1 mole of barium is going to be 137 grams then. 137 grams of barium. All right. So we know that 2, right, Faradays produces 1 mole or 137 grams of barium. All right. Now 2 Faradays, right, 2 Faradays is 2 times, if we convert the Faraday to coulombs, 2 times 96, all right? So 2 times 96,500 is of barium, all right? But we used only 600 coulombs. So therefore, 600 coulombs would produce what mass? All right? What mass? That's what we're trying to find out. All right? I know that some of you love to do a lot of working. I've done a lot of reasoning and arrived at one calculation. Well, I know some of you will convert your Faradays to coulombs first, and then convert, or so you might convert your coulombs to Faraday and then do your calculation. No matter. Do what makes you comfortable. All right? Whatever you're comfortable with, whatever method you're comfortable with, as long as you're following correct procedure, all right, you'll be fine. All right, so we can, I'm going to shift this across to here. All right, so if we do a little bad technique math, cross multiply, x is going to be equal to 600, all right, times 137, all right, over 2 times 96,500. All right. All right. So if you do that on your calculator, you can tell me what you get.
Okay, seeing some answers. There's 0.426, 0.43, 0.43. Somebody before had gotten some 47, something like that. 47.2. So 0.426, 0.43 grams.
Okay, 0.426. All right, that's what I am getting. 0.426 grams. That's what I'm getting. All right. There you go. I see it's 4:36. Dr. Campbell, can I go another question?
Well,
let's finish up this one. Let's finish up this one.
Yes, you can finish up that one.
List 2 factors which can, in general, affect the products formed during electrolysis of compounds. List 2 factors that can affect the products in general, affect the products formed during electrolysis. There are 3 factors that we did, so you can tell me 2.
Of course, in the chat, there is type of anode, concentration of electrolyte. That's the only response I see so far. Concentration of the electrolyte, nature of the anode, and concentration.
Concentration of electrolyte?
Yes.
You're overthinking it, man. You're not overthinking it. That's correct. What about
and somebody says also
type
the
of
series.
electrode?
Yes, type of electrode. Position on the ES.
Electrochemical serum. All right. All right. That's what we're looking for.
Right.
Position in the electrochemical series. All right, good. That's better. All right. State one reason why the reaction of barium water is okay. Okay, that question not cut off. We can stop here. Last part, copper electrode. A current of 3.0 amps is passed through the solution for 10 minutes. Copper is deposited at the cathode. Define the terms electrolysis and cathode. All right, talk to me. Anybody want to give me a definition for electrolysis out of your head, or what you understand electrolysis to mean, to be?
Nothing yet. Okay, so somebody has the decomposition, I think, of an electrolyte. The process by an electrolyte is decomposed by an electric current. You're breaking up. Electrolysis is the breaking of a compound with the passage of a current. Yeah. Yes.
One, right? So electrolysis, yes.
Decomposition of an ionic solution compound. So molten solution. Splitting an ionic compound into its non-metal and metal ions using an electric current. All right.
Don't go too detailed now, be careful. All right, so electrolysis is decomposition of a substance using an electric current. All right, don't get too detailed in there, or else you might get yourself in trouble. All right, what about cathode? How do you define the cathode? What do you say the cathode is?
Is a negative electrode from one response. Negative electrode. Cathode is negative electrode. Somebody says cathode is connected to the negative terminal of the battery. You're breaking up a bit. Somebody says cathode is the part that emits the electrons. Yes, sir, you're breaking up. Sir, I'm not hearing you if you're speaking.
So, folks, the best definition for the cathode is actually, you hear me?
Could you repeat, sir?
Yeah, I'm saying that the cathode is the site of reduction. That's yeah, so I'm saying that the cathode is actually the site of reduction. That's the best definition. Or if you're going to say the negative terminal, you must say during electrolysis, all right? If you're going to say the negative electrode, you must add during electrolysis, all right? All right, okay, so there you go. All right, so last thing here now, calculate the mass of copper that is deposited during the reaction. The mass of copper that is deposited during the reaction. So I'm going to just write this out. I'm going to do that right here. Let's get this out. Let's get it out of here. All right, get that a little bigger. All right, so let's go. So it says during electrolysis we had what? 3 amperes passing through for 10 minutes. All right, so we can first of all work out first of all the quantity of electricity passing through. Q is equal to IT. All right, so we have 3 amperes for 10 minutes. We have to convert the minutes to seconds by multiplying by 60. So that is giving us 1800, is it? Coulombs. All right, you can go ahead and confirm that. All right, now copper, 2+ ions, are going to gain 2 electrons, and they're going to form copper metal. All right, there you go. All right, now this is telling me that 2 Faradays here of electricity produces 1 mole of copper, and the relative atomic mass of copper is 64. That means that 1 mole weighs 64 grams. All right, so 2 Faradays produces 1 mole or 64 grams of copper. All right, so therefore, if we convert the Faradays to coulombs, right, 1 coulomb is 96,500. Sorry, 1 Faraday is 96,500 coulomb. So we can say that, therefore, if we convert this to coulombs, would multiply by 96,500. So therefore, 2 times 96,500 coulombs is producing 1 mole or 64 grams of copper. Okay? But we only passed 1,800 coulombs. So let's see, what are they saying in the chat? What are they getting there?
Okay, so the answers we're seeing, somebody sent 0.59 grams, 0.6 grams. Those are the answers so far.
Okay, good.
0.597 grams of copper. Yes. And we have a few more like that of 0.597.
All right, so we're seeing that we're getting some consensus there.
0.6.
So depending on how much rounding off you did. All right, so there you go. So we're saying that, just to recap, all right, we first find the quantity of electricity that passed through, and that is given by the current times the time in seconds. So that's 3 amps times 10 minutes. To convert the minutes to seconds by multiplying by 60. You get 1,800 coulombs. And then you go to the half equation to figure out the relationship between the charge that produces a certain amount of the substance deposited. And here you can see that 2 moles of electrons have to pass to give you 1 mole of copper. Therefore, 2 Faradays produces 1 mole of copper, which has relative atomic mass 64, so it has molar mass 64 grams. All right, so 2 Faradays produces 1 mole of copper, which weighs 64 grams. And I just converted to grams because the question asked me about mass. If the question had asked me about moles, I wouldn't bother with the 64 grams. I would just work in moles. Okay? So I'd say, okay, since this question is asking me for mass of copper, right? Question is asking for mass of copper, I convert the moles to mass right away. Okay? So once I get, okay, that's 64 grams, I convert the Faradays to coulomb because you have to use the same charge units. All right, I could have converted the coulombs to Faradays and then work in Faradays. It doesn't matter which one you do, as long as you do it accurately, you should be fine. All right, so therefore, now 2 times 96,500 coulombs gives me 64 grams of copper. And then I allowed 1,800 coulombs to flow. So I can then work out what mass of copper would that correspond to, or would be formed from that. And there's my calculation. So I have 1,800, and I'm doing it on my calculator now as I speak to you. All right, divide by 96,500. All right, equal. All right, and I'm getting 0.596, just like you people. So I'm getting 0.597 grams. All right, a gram. Okay. That's it, folks.
Okay, sir. Could you repeat that statement?
So I just take a couple questions and I think we're gonna have to end it here.
Right. Colleagues, students, if you have any questions, anything you weren't clear on, you can raise your hand and we'll allow you to ask Mr. Miller. Okay, I'm not seeing any. Okay, so
All right,
there's a
good.
raised hands.
I see
Just give me a sec.
Christine Lane, I see oh, this was really helpful. Okay, there's just some comments. Ken Garfield, Douglas raised his hand.
Yes,
Yeah,
yes, you
I
can
have a
go ahead.
question.
Yeah, go ahead.
There was this question about the solution being alkaline. There was a question where the solution became alkaline. Could you explain why it would become alkaline?
Okay. All right, so let me go back to that one. Give me a second here. Let's just click on that one. What's this one? This one. All right, yes. So, okay, so this was a question. Question said, are you seeing it? Right here. Yes, I think you're seeing it. It says when aqueous lithium bromide is electrolyzed, a colorless gas is formed at the negative electrode. That's the cathode. And the solution becomes alkaline. Explain these observations and include an equation. And the negative electrode, this is aqueous lithium bromide. So what we were saying is that, right? Let's just think about what is at the and what would go towards the cathode, the negative electrode. It would be the positive ions, which would be lithium and hydrogen. Now, lithium being a reactive metal in group 1 would be high up in the electrochemical series. So hydrogen would be preferentially discharged. So that is how you get the colorless gas. The H plus ions are discharged. So the equation would be this equation that they're looking for. 2H plus 2E minus gives you H2 gas. Okay? So that's the first thing. But then, so you explain these observations. So hydrogen gas, so you would say hydrogen gas is produced at the cathode. And this is the equation that you would give them. Now, in order for you to get an alkaline solution, it would mean that you would also be getting rid of the bromide. Because the alkaline solution would be a hydroxide, a metal hydroxide. That's where you get the alkaline solution. All right. But the question doesn't directly ask you about that. But we speculate based on that, based on the question, we'd have to be getting rid of the bromide at the anode. All right. So we don't have to write the equation for that. But in order to get the alkaline solution, you get the bromide at the anode. All right. So that's what we said. All right. So the question missed out a little thing here. Here you should have said concentrated lithium bromide. But by right, they didn't have to tell you because they didn't ask you about that. They didn't ask you about that. You could have answered the question. You could have explained the negative. They could have explained. They could have explained. You could have explained the negative. The colorless gas being formed at negative electrode. And it's only when you're explaining why the solution becomes alkaline, you need to say that the bromine is discharged at the anode, right? So you wouldn't have to. They didn't really have to tell you, but it would have been helpful. I hope that helps.
Sir, somebody's asking, two questions. What if they ask you to find the mole and not mass? That's one. And somebody's asking about this reaction. Is this like a displacement reaction?
No, this is not a displacement reaction. All right, because it's not that the ions are being swapped. This is a redox reaction in which you're changing the nature of the substances, right? So this is lithium bromide solution, right? And you're ending up losing hydrogen and bromine, so you're ending up with lithium hydroxide left in there. So it is not a displacement reaction at all.
Okay. All right. Okay, so the person who asked, are you clear on why it is alkaline now?
Yes.
Okay, good.
Like somebody
Beautiful.
was asking about moles. Nasty.
Okay, somebody's saying for this question you said earlier, reddish brown gas being given off. What is that? I guess you just
Bromine.
That is bromine. Mhm.
All right,
Okay.
somebody's asking if calculate is in moles instead of grams. What if they ask in moles? Well, if you ask in moles, you just use moles.
Right,
Right?
right.
For example, if they ask you in moles, you just work in moles. You just ignore that altogether. You just say, okay, moles. Um, you just say, okay, 1 mole Cu, therefore 1 mole Cu, right? So X mole Cu, and instead of doing all that, instead of 64, you multiply by 1 mole, and you get your answer in moles. All right.
All right. Any other questions? You raise your hands if you have a question for Mr. Miller as we wrap up. If there's anything that you didn't get. All right. Okay, so there's Janelle. Okay, Janelle, go ahead.
Okay, I was asking, sorry, why is the bromine displaced instead of hydroxide? Why does the hydroxide remain in the solution and it is more, it is at the bottom, that means it is easier to discharge than
All
the
right. So,
bromine? Why is
so that's
that
why we're
so?
saying that in this. Okay, so that's what we're saying, that in this solution, it would have to have been concentrated lithium bromide, right? Right? But the fact that they tell you that the solution becomes alkaline is that they're telling you that the hydroxide remains in the solution. That means the bromide is being discharged.
Okay.
So what we're saying is that the solution, this electrolyte must have been concentrated.
Okay, sir, thank you.
All right, just to mention one last thing. Because I think this is important, because an important little outlier is, and it's related to what we just did a while ago, is the electrolysis of concentrated sodium chloride solution. Inert electrodes. So concentrated sodium chloride solution is kind of different. You have to be very careful, because the sodium is going to give you sodium ions. Sorry, sodium chloride is going to give you sodium ions and chloride ions. But of course, the water is going to give you hydrogen ions and hydroxide ions. Now, it's concentrated, all right? So although the hydroxide is lower in the electrochemical series, because this is concentrated, the chloride is preferentially discharged. All right, so the chloride would be discharged, would give up electrons to form chlorine gas, like that. But when you come over to the cation side, however, if you follow the same rule, then you should expect the sodium to be discharged. But that doesn't happen. The hydrogen ions are discharged. And that's because of the sheer difference in position in the electrochemical series. Is the fact that sodium is all the way up the top and hydrogen is so far down that even though the concentration of this is high, it is not enough to override the electrochemical series. Now that's a kind of simplistic explanation I'm giving you. In fact, it has to do with, again, principles of equilibrium and the actual electrode potential measurements, which you are not you're not at that level yet. All right, but you just have to remember this one, that even though you have a concentrated sodium chloride solution, on the anion side, the rule is followed. The higher concentration causes even though the chloride is high in the electrochemical series, it is still discharged. But The hydrogen is not discharged in preference to the sodium. That's just one that you have to remember, okay? Yes.
Someone is asking if it only applies to sodium chloride, or you can say to,
No, it doesn't.
to halide.
No, it doesn't. No, it doesn't. It doesn't only apply to sodium chloride, but for your syllabus, effectively that's it. But it would apply to other very reactive very reactive metals, right? But don't worry about those, right? Worry about what's on the syllabus.
All right. Okay, students, colleagues, we want to thank Mr. Miller for helping us to get a better understanding of electrolysis. Help me to thank him right now in the chat. All right, if there's one lingering question, if you're burning and you don't want to leave with a question, you can go ahead and indicate. If not, please use the reaction button. Thank Mr. Miller for helping you out this afternoon. All right. Thank you, sir. All right, so remember this, this is on the YouTube channel. You can always type in Chemistry Camp Day 4 and you'll see all the videos that we have done so far. All right. Mr. Miller, thank you.
All right, it's a pleasure. And I hope that you will all be very successful in your exam and that this process was able to help you to do that.
Right, so remember that we have another session next week, Friday, to complete the organic chemistry. All right. So that's our final CSEC session next week, Friday, for organic chemistry. All the best in your exams. All right.
Bye-bye.
Very good. Okay, thank you, sir.
All right, thank you. And I think we had fun.
Yes, yes, I hope so. Hope it was meaningful. We'll talk.
All right.
All right, blessings, blessings.